Welcome to lecture 10. I am Professor J.N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is Module 3, lecture 10. Now I will begin these geosynthetics properties and test method. This outline of the geosynthetics and test properties is introduction, properties of geosynthetics, that is physical properties, mechanical property, hydraulic properties, endurance property. Geosynthetics clay liner, which is called GCLS, properties and test method. Tensile strength of nanomaterial. Ultimate versus allowable geosynthetics properties. So I will cover this during this lecture number 10 on the course Geosynthetics Engineering in theory and practice. When to test geosynthetics? Firstly, for any project, the design engineer must check the required specification of geosynthetics material. Without knowing proper specification, it is very difficult to select the correct geosynthetics for any specific project. It is needed to conduct tests on geosynthetics from an independent laboratory. Generally, test results are supplied from manufacturer data sheet. These data sheet provide minimum average roll values, that is MARV, for quality control of geosynthetics material. Considering environmental impact, geosynthetics should be collected from the project site and sent to geosynthetics laboratory for testing of the different properties. Main strong reason for exploring this exciting new engineering construction material in civil engineering are as follow. It gives excellent stress strain behavior, good flexibility, excellent filtration characteristic, high water permeability, excellent mechanical property, can be welded together, does not form byproduct, high resistant to climate condition, high resistant to chemical and biological attack, chemically ultraviolet stabilized. Time, cost, rapid construction, environmental friendly, sustainability and durability. Tests on geosynthetics are conducted in two different ways. A indirect test or in isolation test. Tests are performed only on geosynthetics material itself, and B performance tests are performed along with site specific soil. Now we will discuss the properties of geosynthetics, their physical properties, mechanical properties, hydraulics property, endurance property. So we will discuss the different types of the geosynthetics material. It may be open geosynthetic material, non-open geosynthetic material, it may be geogrid, it may be geomembrane, it may be geosynthetic clay liner, it may be geocell, and we will teach you about their different properties. So first of all, I will talk about the physical property. In the physical property, we require what is mass per unit area or weight, what is thickness, what is specific gravity, what is stiffness or flexural rigidity or the flexural stiffness. So we should know that how to conduct the test. This is very, very important for quality control and quality assurance. So mass per unit area as per STM D 5261 So 5 test specimens are to be weighted in a weighting machine, accuracy of 0.01 gram, and average value is recorded. Test sample are of size 100 millimeter into 100 millimeter, and the unit is expressed as gram per meter square. Cost of the geotextile is directly related to the weight of the geotextile material. You can see here, this is the geotextile sample is 100 meter by 100 meter. This is another also type of the geotextile material, and then you can place on this machine, and then you can find out what will be the weight, and the accuracy of this machine is of 0.01 gram. So it is very simple test, and you can measure the what will be the weight of the geosynthetics material. And because if you need more weight, that means cost of the geotextile automatically will be the more. Next property is thickness, STMD 5199. Geotextile exhibit different thickness according to the different pressure. The thickness is measured to an accuracy of 0.02 millimeter under a specified pressure of 2 kilopascal, and sample size is 200 millimeter into 200 millimeter. The thickness is generally in the range of 0.25 to 8.5 millimeter. The thickness of geogrid and geomembrane are measured under a normal stress of 20 kilopascal. You can see here thickness measurement in a geotextile. You have to place this geotextile material here, and whose size is 200 millimeter into 200 millimeter. So this is 200 millimeter by 200 millimeter, and this weight of this is 2 kilopascal under a specified pressure. So you have to place under a specified pressure of 2 kilopascal. So you can take a 5 sample and you apply the load, and then you measure that what will be the change before and after applying the load, and then you measure the thickness, and this thickness is lies between 0.25 to 8.5 millimeter. So when you are measuring the thickness for the woven and non-woven geotextile material, then you are applying the pressure of 2 kilopascal, but in case of the geogrid or the geomembrane, you can go under a pressure of 20 kilopascal. Now specific gravity as per STM D792 or D1505, specific gravity can be defined as a ratio of the unit weight of the material to the unit weight of distilled water at 4 degrees centigrade. Specific gravity of different geosynthetics material, you can see here that if it is a polypropylene material, specific gravity is 0.91, polyethylene material specific gravity is 0.9 to 0.96, polyester PET the specific gravity 1.22 to 1.38, polyvinyl chloride PVC specific gravity 1.69, nylon specific gravity lies between 1.05 to 1.14. So different material have their different specific gravity. Now the stiffness or flexural rigidity or flexural stiffness as per STM D1388. So geotextile specimen is 25 millimeter wide strip, and geotextile is placed along the length of a horizontal plane and bends gravitationally under its own weight on an inclined plane, making at an angle of 41.5 degree with the horizontal, and then you can measure what will be the stiffness of the geotextile. Stiffness of the geotextile is L by 2 whole to the power q into W, where this L is equal to length of overhang geotextile and the bending length is L by 2, and this expressed is centimeter, and W is the mass per unit area weight, mass per unit area, and which expressed as mg per centimeter square. So therefore, the stiffness of the geotextile or unit of stiffness is mg centimeter. So do not confuse that what we are talking about the stiffness of the geotextile material. So stiffness of the geotextile unit is mg centimeter. So you can see here, this is the L length of the overhang geotextile. Okay, this is in centimeter and the weight is mg per centimeter. So unit will be mg centimeter. So minimum thickness stiffness of geotextile depend on various degree of required workability, that Halliburton et al. 1980. The property is important in the field workability requirement for installation of geotextile. If the soil is very poor or California bearing ratio value is very less, the stiffness of the geotextile required is very high. So when we select for any project what should be the stiffness of the geotextile material, that also depend upon that what will be the type of the soil, what will be their California bearing ratio or unlaid shear strength. So these are all I talk about the physical property. Now we will address the mechanical property, which we will cover compressibility, tensile strength of geosynthetic material, brush strength test, puncture resistance test, penetration resistance test, or drop test or drop con, it is called impact strain, TR impact resistance, tensile behavior of geogrid material, tensile strength of gabion, direct shear test, pull out or anchorage resistance, tensile strength of geomembrane, TR resistance of geomembrane. So what is compressibility? Compressibility indicates the reduction in thickness under applied pressure. Compressibility of geotextile depends on its thickness and mass per unit area. As the pressure increases, thickness of non-woven needle punched NWNP and resin bonded geotextile get reduced significantly, and accordingly the transmittivity get reduced. Compressibility of woven and non-woven heat bonded geotextile or NWHB is low. Compressibility of non-woven needle punch geotextile play a very important role, as most of the time we use this type of geotextile to pass the liquid along the plane. You can see this figure, that is related between the geotextile thickness in millimeter and this is the applied pressure in kilopascal. You can see there are two types of the geosynthetics material, how the variation in thickness of geosynthetics with change in the pressure. This is non-woven heat bonded material and this is non-woven needle punched material. You can see this is non-woven needle punched material and this is non-woven heat bonded material. So it is clearly observed that non-woven needle punched geosynthetics are more compressible. Tensile strain, there are various types of the tensile strain, that is wide width tensile test, that is STMD 4595 and ISO 10319, very wide width tensile strength test, narrow strip tensile strength STMD 4751, shear seam strength of geotextile STMD 4884 and ISO 13426, graph tensile strength STMD 4632, trapezoidal TR strain test. So you can see that this is the wide width tensile strength as per STMD 4594. The size of the sample that is 200 millimeter by 100 millimeter. So, this type of strain test is highly recommended, because we adopt the tensile strength value of all the geosynthetic material based on the wide width tensile stress. So, here gauge length about 100 millimeter. You can see that we have conducted some test on the non-woven geotextile material, even the woven geotextile material. You can see in case of the non-woven geotextile material how there is a formation of neck, and also in case of the woven geotextile material you can see that typical failure pattern. So, we can obtain from the test what will be the tensile strength of the geosynthetic material and what will be the corresponding that elongation, and this is the test result on thermally bonded non-woven geotextile material. And whenever you will conduct the test, you are to maintain the machine strain rate. The machine strain rate is 10 plus minus 3%. The reason for the necessity of wide width specimen is that geotextile, particularly non-woven, achieve high Poisson's ratio value from narrow steep test. The tensile strength of the geotextile, which is designated as T geotextile, can be expressed as force per unit width. So, T geotextile is equal to Fb by W. So, strength of the geotextile is expressed as kilonewton per meter, where Fb is the observed breaking force in kilonewton and W is the specimen width, that is in meter. That is why the tensile strength of the geotextile is expressed in kilonewton per meter. So, you remember it is kilonewton per meter, not kilonewton per meter square. There are also other very wide width tensile test. For design purpose, very wide width tensile test is not recommended. You can see this is the width of the sample about that 1000 millimeter, and this is about 0.5 times of W. So, this test is not recommended. Then narrow steep tensile strength as per STMD 1682. So, here it is a very narrow, you can have maybe 25 millimeter or 50 millimeter, and this gauge length about 75 millimeter, and strain rate is 300 millimeter per minute. You can see this is the size of the test sample with the test assembly, and you have to perform the tensile strain appear low compared to the wide width tensile strain. So, this kind of the test not recommended. So, we always recommend that wide width tensile strain for geosynthetics material. So, here shows the different tensile modulus from typical stress strain curve. So, how you can calculate the initial tangent modulus, offset tangent modulus and the second modulus. In the first, this is the tensile strain and this is the strain, and you can see the nature of the curve. This is the stress strain curve for geotextile material. So, you can draw a initial tangent from the origin, you can make a slope. So, you can determine what will be the initial tangent modulus. These data also will be very useful for the design and also for the computation of the problem. Now, from this slope you can determine that what will be the initial tangent modulus of geotextile. Now, sometimes you can see if you perform the test, you can have a nature of the curve is like this. That means this is a something offset modulus. You can draw from this straight line and you can make at an slope here, and this is the offset. So, this is the stress strain curve for the geotextile, and this is the relation between tensile strength and the strain. So, you can also determine what should be the offset modulus I will show you one of the example and how you can calculate the offset modulus. And this also figure shows the relationship between tensile strength and the strain, and you can see this is the nature of the curve for the geotextile material, and we wanted to calculate that what will be the second modulus. So, you can take any point on this curve and then you can take a slope of this, which will give you that what will be the second modulus. Also in many design we use for the second modulus. So, this is the ratio of the stress and the strain, which will give you that second modulus. So, in this slide we have shown the different tensile modulus for the typical stress strain curve. This figure shows the tensile strain versus strain curve for different geotextile material. These are the tensile strength in the y axis and strain in the x axis. Three different types of the material. One is non-woven heat bonded material, non-woven needle punch material, number 2, and number 3 woven needle punch material. So, these are the three curves are shown, sample number 1, sample number 2 and sample number 3. And the right hand side in case 2, here also have shown the tensile strength versus strain relationship for the 3 geotextile sample, that is non-woven heat bonded number 1, number 2 non-woven needle punch geotextile material, and woven monofilament geotextile material. You can see that different nature of the stress strain curve for the different type of the material. Now, we wanted to calculate that how you can determine the initial tangent modulus, or how you can determine the second modulus at a particular strain. For example, if you want to determine second modulus for a 20% strain for this sample number 1. So, for the 20% strain you can calculate what will be the tensile strain. So, let us say about 12 kilonewton per meter for the strain of 20%. Similarly, for this sample also you can determine what should be the initial tangent modulus. Also you can determine that for the sample 1 what should be the maximum tensile strength value for the sample number 1. So, this is the strain, this is about 45% strain, and corresponding the maximum tensile strength value about 30 kilonewton per meter. I am showing it here for sample number 1, maximum tensile strength T maximum is 30 kilonewton per meter and maximum strain epsilon g is equal to 45 degree. From here we can calculate. So, this is 45 degree for sample number 1 and corresponding tensile strength value is 30 kilonewton per meter. Now, initial tangent modulus. So, initial tangent modulus E is equal to initial slope of the curve. So, initial tangent modulus means this is initial slope of the curve, this is initial slope of the curve. So, correspondingly you can determine that what will be the tensile strain and corresponding the strain value. So, you can see that is the initial tangent modulus, and about near about here 12 and corresponding strain value is 0.08 and this strain. So, he can have 12 by 0.08 is equal to 150 kilonewton per meter. Now, toughness which is designated at Tu is equal to half into T maximum into epsilon g. Now, toughness is equal to half into T maximum is 30 and epsilon g is 45%, that means 0.045. So, this is equal to 6.75 kilonewton per meter. So, from the case 1 for the sample number 1, so we observe that how you can calculate the second modulus, how you can calculate the maximum tensile strain, and also how you can calculate the maximum strain value. And at the same time for the sample number 1, we have calculated what should be the initial tangent modulus and also corresponding strain. So, if you know the initial tangent modulus and maximum tensile strain for the sample number 1, then also you can determine that what will be the toughness. So, that toughness is equal to half into T max into epsilon g. Now, I am showing for sample number 2, and you see there are 3 sample 1, sample 2 and sample 3. So, this for the sample 2 you can see nature of the tensile stress and strain curve is like this. This is for sample 2 is like this. So, this what we call the offset. This is the offset modulus, this is offset modulus. So, the slope of this will be the offset modulus. So, we want to calculate what should be the offset modulus and what should be the initial tangent modulus. This is the curve for the sample number 2. So, this is the initial tangent modulus. You can see this is the initial tangent modulus. So, initial tangent is what any strain and you know corresponding strain. So, for the sample number 2 or case 2, we want to calculate initial tangent modulus E is equal to 8 by 0.50. You can see this is the initial tangent modulus and this is the 8 tensile strain value and corresponding to strain value is here. This is near about in between 40 to 60. So, it is comes about 50. So, 8 divided by 0.50. So, initial tangent modulus will be equal to 16 kilonewton per meter. Now, how we can calculate the offset modulus? This is offset modulus, this is offset modulus, this slope. So, this is the 20, this is 20 and we are taking this slope, so we are taking this point. So, this is 20 and this is in between 20 to 40. So, this is 31 and corresponding tensile strain value is 20. So, if this is a 31, so this 20 divided by 31 minus 20 will give you ratio will give you that offset modulus. You can see that offset modulus is equal to 20 divided by 0.31 minus 0.20 is equal to 181.8 kilonewton per meter. So, second modulus at 40% strain you can designate it at E40 is equal to 34 by 0.40. So, you can go second modulus value. You can also calculate that what will be the second modulus value. Suppose this is the for 40% strain, this is the for sample number 2, case 2 and corresponding you can see what should be the tensile stress value. It also lies between 30 to 40. So, that is why it is coming 34, this divided by 0.40 because this 0.40 is the strain. So this will be equal to 85 kilonewton per meter. So for the sample 2 or case 2, we calculate what will be the initial tangent modulus, how to calculate offset modulus, and also we show how to calculate the second modulus at a 40% strain. So any strain you can calculate the second modulus. So when we will perform the tensile strength of the geotextile material, we also have to perform the seam strength of geotextile. Here we have shown that seam strength of geotextile as per STM D4884 and ISO 13426. So this is the size of the sample. This is 200 millimeter and this is 100 millimeter. It is like a wide width tensile strength sample, but in case of strain sample you have to be projected by 25 millimeter by 25 millimeter, and this middle portion is the seam. The sample has been joined by teaching, so it has been teached, and this sample has been performed the strain seam state in a universal testing machine at a strain rate of 10 plus minus 3% per minute, and unit of the seam strength is kilonewton per meter. So you have to check what will be the tensile strength of the geotextile material without and with seam strength, and from that also you can calculate what will be the efficiency of the geotextile material. I have already told you about the how to calculate the efficiency. So if you know the tensile strength of the geotextile material, and if you know the tensile strength of the shear stream of geotextile material, so you can calculate. Now when you will join the geotextile material in the field, there are different types of the joining. One is the butterfly seam type, that is SSD2, or it may be the your J seam type SSM2, or flat or pair seam type SSA2. So you can see that how the butterfly, it is like a geotextile material and then wrap, this side also geotextile material wrap, and then you can stitch at a particular spacing 20 millimeter. So this is called the butterfly, and this is J seam, it looks like a J. So this is one geotextile material and this is another geotextile material, and then attaching it here. So this called the J seam type joint, and this one is like a flat or like a pair. So this is the geotextile material, this is the geotextile material, and then are teaching, two layers of stitching at a particular spacing 25-40 millimeter or like that. So you have to stitch properly, and you have to use proper kind of the material for teaching. So what you will use, whether you will use polypropylene, polyester, nylon. So you have to provide with the very good strength of the fiber element for stitching, or thread for stitching. So most of the cases it has been observed that butterfly is recommended for the teaching. Of course nowadays you can weld the non-woven geotextile material. So seam strength efficiency can be expressed as AC is equal to T of seam divided by TG into 100%, where T of seam mean wide width seam strength as per STM D4884. So you can calculate what will be the seam strength, and Tg is wide with geosynthetic strength without seam as per STM D4595. So, you know for the what will be the wide with geosynthetic strength without seam, and then you know what will be the wide strength for seam strength. So, you take the ratio into 100%, which will give you that what will be the seam strength efficiency. So, you know the what is seam net efficiency. Next, we will talk about the graph tensile strength as per STM D1682. So, this test, you can see the sample like this, and here is size is about 50 millimeter, and in between is 75 millimeter, this again the 25 millimeter, and this is the clamp, this will be clamp, this will be clamp, and this is 100 millimeter and this is 200 millimeter, and then you have to clamp here like this, clamp here. This is the test have been conducted in IIT Bombay, and this you can see that before test, and you can see that after test. So, this test relies on the filament interaction in geotextile material. For non-woven geotextile material, the effects are more than the woven geotextile material, and the graph tensile test is reported in kilonewton, not in kilonewton per meter. As the sample is partially clamped, you can see that here sample is partially clamped, this portion only clamped. Stress is not propagated the entire width, only this portion stress is propagated, not the entire width of the sample. So, it is unusual test and widely misused. So, graph tensile strength should not be used as a design parameter. Now, we will address the analytical analysis of graph tensile strength. Now, what is happening in the field and how we can analog in the experiment. So, this is analog of graph tensile strength in the laboratory, and this is field method for graph tensile strength. So, you can see here this is Li, that is initial strength, length of this. If this is the aggregate, this is the aggregate, and on the top of this is aggregate, and AP is the applied pressure, and this is D, and this is also D, this stone or aggregate, and in between is equal to D of 2, and this is the subgrade, and geotextile is placed between this aggregate and the subgrade. So, initial length is L, this is showing this initial length Li, length of the geotextile material, this is Li initial length of the geotextile material, and this is the D, D is the diameter of the stone. So, this is diameter of the, this is diameter of the stone, all three diameter of the stone, and here is AP, see, applying the pressure. If apply the pressure, then you can see here how is the lateral in plane deformation after application of load, after application of load on the upper stone. So, if you apply the load on the upper stone, then you can see the how stone is laterally deformed, and this you can say LF length, you can see that LF is the final length of the geotextile, this is LF is the final length of geotextile. So, look at here that this Li, that means initial length will be, this is d by 2, I am showing that d by 2, and then this also d by 2 and then d by 2. So, this will be d by 2 d by plus d by 2 plus d by 2, and Lf is the final length of the geotextile, that means this final length of the geotextile Lf, that is d, this is d by 2 and d by 2. So, you can write d plus 2 d by 2. So, that is why you are writing d plus 2 d by 2. This is the final length of the geotextile. So, without any breakage or the slippage, maximum strain in the geotextile can be expressed as epsilon is equal to If minus Lf minus Li divided by Li into 100. So, we know that Lf is equal to final length d plus 2 d by 2 and minus that initial length of the geotextile, that is d by 2 plus d by 2 plus d by 2. So, this is d by 2 plus d by 2 plus d by 2, this divided by the final length of the geotextile material. So, this will be equal to 3 d by 2. So, if you calculate, then you can have that epsilon is equal to 1/3, means it is about 33%. Now, Giroud give a equation for the determination of required graph strength. So, that is T required is equal to AP into d V square into epsilon. This is given by Giroud 1984, and T required is the required graph strength, AP is equal to applied pressure, what you are putting the pressure AP, and dV is equal to maximum void diameter. So, maximum void diameter is equal to 0.33 of dA, where dA is equal to average stone diameter. So, if you know that what is the average stone diameter dA, so you can calculate the what will be the maximum void diameter. So, if you know dV, if you know epsilon, and if you know what is the applied pressure, then analytically you can determine what will be the required graph strength of the geotextile material. Here one example has shown the tar inflation pressure is equal to 650 kilopascal, average stone diameter is equal to 50 millimeter. Assume the geotextile is pressed beneath the stone base course and calculate the required graph tensile strength of the geotextile. Assume 50% of total ultimate graph strain will be mobilized. So, now go for solution. We know that total ultimate graph strain is 33%. So, what should be the mobilized graph strain? 50% of the total. So, 50% of the total graph strain means 0.33 into 0.5 is equal to 0.165. What is T required? T required is equal to, you have seen the earlier equation, AP into dV square into epsilon. So, here what is AP, that pressure, that is 650 kilopascal into dV square. So, dV square will be equal to dV square will be equal to 0.33 times that 0.05. So, because dV is equal to 0.33 of d of A, d is equal to average stone diameter, and average stone diameter here is 50 millimeter. Okay. So, dV will be equal to 0.33 times of 0.05, because this is the stone, that is the diameter, average stone diameter. So, average stone diameter is 50 millimeter. So, that is why this, from this equation dV square d maximum void diameter 0.33 dA. So, dA is this, 50. So, that is why 0.33 into 0.05 whole square into what will be the strain value. Strain value is 0.165. So, this will be equal to 29.2 Newton. So, from this test analytical, so we can also calculate what would be the graph strength value. Now, we will discuss trapezoidal tear strength test as per STM D4533 and ISO 13434. So, trapezoidal shear strength is generally measured in Newton. You can see this is the sample, and in this specimen this is about 100 millimeter and this is 200 millimeter. So, it looks like a trapezoid like this, and in between this is about 25 millimeter and there is a cut is 15 millimeter. So, this trapezoidal is to be clamped like this, and this test is done to tear the test specimen from the point of initiation here. So, tear strength is important when the geosynthetics is damaged. So, one has to conduct the tear strength. Next, burst strength test. So, you can see here different types of the burst strength test apparatus, and this Mullen burst strength, ball burst strength, severe burst strength, Mullen burst strength as per STM D3786, ball burst strength as per STM D751, severe burst strength DIN 54307E. So, in case of this Mullen burst test, you can see there is a hydrostatic pressure and the geotextile sample with the geomembrane is just to clamp here, and hydrostatic pressure is pushed from the bottom, and this geotextile material is burst, and you can measure what will be the pressure. Also, you can go for the ball burst and the severe burst. So, this is a equipment in which also you can also determine the burst test. This is also modified severe burst, and this you can see this rod and geotextile material is clamped here, and you have to push, and then there is a pressure meter. You can measure the pressure, at what pressure the geotextile material is burst. So, you can calculate this burst pressure. So, now how you can analytical analysis for the burst strength test. Burst strength is required to design the geotextile for separation. Geotextile may burst due to the applied upward load. You can see here that how you can compare the field model of burst resistance to the laboratory simulation. So, here is the subgrade, here is the geotextile material, here is the stone aggregate. Now, in the stone aggregate there is a void in the stone. When due to the traffic load or the wheel load, this geosynthetics material may push into the void of the aggregate. So, you can see that what is happening in the field, if you can simulate this. So, you can see here is the aggregate, here is the aggregate, here is the void between the stone, and due to the application of the wheel load or the tar pressure, this geotextile material push into the void of the aggregate, and the geotextile material may burst, which in the field can be simulated in the laboratory. So, it is you can clamp in a model, and you can see this is geotextile material, it may push the upward, and then geotextile material may fail. So, this way we calculate the brush test. Now, some theoretically from the field concept, 1984 developed a formula required for geotextile brush strength, that is T required is equal to half into Pg into dV into epsilon g. So, you can see here this is the Pg and this is the d, and there will be the strain in the geotextile depend on the width of the void, that is Wb, and the deformation of the void is Zw. So, this strain you can calculate with this equation, epsilon g is equal to 1 by 4 2 Zb by Wb plus Wb by 2 Jb. What this Jb is the deformation of the void, and this Wb is the width of the void. So, you can calculate that what should be the strain value, that means epsilon g. Now, Boolean brush test can be analog to the field condition. So, this is the experimental model setup for brush strength in the laboratory, and this is the dB, which called the diameter of the burst equipment, and this equal to about 30 millimeter, and this is the geotextile material clamp, and there is a upward force, that is Pb. This is what you call the brush strength. So, geotextile is pushed upward and it form a hemispherical shape as well as fell due to radial tension. So, ultimate strength of the geotextile can be written as T ultimate is equal to half into Pb into dV into epsilon g, where Pb is the burst strength and dV is the diameter of the burst equipment, this in the laboratory, this equipment, and that is known value, that is 30 millimeter diameter, and epsilon g is the strain in the geotextile. So, we can calculate that what will be the allowable tensile strength of the geotextile, that is the ratio of ultimate tensile strength and all cumulative reduction factor. I will discuss more about the cumulative reduction factor. Let us say that cumulative reduction factor is 1.5. So, you can calculate factor of safety is equal to T allowable by T required. So, we have calculated earlier that what should be this T required value here, half into Pg into dV into epsilon g. So, T required is known and T ultimate also is known. So, you can calculate what will be the T allowable, because T ultimate is known. So, T allowable you can calculate T ultimate by cumulative reduction factor, and this divided by T required, and T required also you have calculated this of Pg into dV into epsilon g. So, we can write a factor of safety T allowable by T required Pb into dV by cumulative reduction factor into Pg into dV. Now, for example, that dV you know 0.33 times this is dA diameter, and dV is equal to 30 millimeter, that is dV is this diameter of the burst equipment 30 millimeter. So, dV also is known 30 millimeter and cumulative reduction factor 1.5. So, we can write that factor of safety is Pb into 30 divided by 1.5 CRP and Pg, and this dV is 0.33 dA. So, if we can calculate Fs is equal to 60.6 Pb by Pg into dA. So, with this equation we can draw this curve. So, we can have a design chart burst analysis of the geotextile considering reduction factor 1.5 and the factor of safety 2. So, this design chart reveal that what will be the size of the stone. This chart shows that what should be the required what is the required burst resistance, and this x axis will show the pressure. at the geotextile stone interface, and this the different diameter of the stone. So, this may be 15 millimeter, 30 millimeter, 60, 90 millimeter, 125, 200, 300 millimeter, like this. So, this design chart reveals that size of the stone aggregate possesses a significant impact on the brush strength of the geotextile. If you know what will be the pressure at the geotextile stone interface, so and then if you know that what will be the diameter of the aggregates, then you can calculate what will be the required brush strength. For an example, let the tar infiltration pressure Pt is equal to Pg 650 kilopascal and maximum size of the stone is 60 millimeter. Determine the required brush strength of geotextile using cumulative reduction factor is equal to 1.5 and factor of safety is equal to 2.0. So, we know that cumulative reduction factor 1.5. So, we know the earlier that factor of safety is 60.6 Pb by Pg into dA. So, we have to calculate what will be the brush strength. This is Pb. So, Pb will be equal to Fs into Pg into ds divided by 60.6, and factor of safety we have taken 2, this is 2, and this pressure is 650, Pg is 650 into dA. dA we know that diameter of the maximum size of the stone, that is 60 millimeter, this divided by 60.6. So, it will give 1287 kilopascal. So, required burst resistance is 1287. You can see for this pressure you can have this 1287 kilopascal burst strength. You can draw, you can also simulate from this curve. You can see that when the that pressure is 650 kilopascal, you can see the pressure is 650 kilopascal and this diameter of the stone is 60 millimeter. So, you can directly also calculate what will be the burst resistance, that is 1.87 kilopascal. So, these are the tests I have just talked about. Please let us hear from you any question. Thanks for listening.